Hey guys, Mr. Backwork here. In this video, we're going to look at the mean value theorem. Now, as we're talking about the mean value theorem, it's a way to connect the average or mean rate of change of a function over a specified interval with its instantaneous rate of change at a specific point within that interval. And what the mean value theorem says is that if you have an interval that runs between some a value and some b value on a differentiable curve, then there has to be at least one tangent line along that AB interval that's parallel to the chord that's created through the points A and B. So here's what the mean value theorem actually says. If y equals f of x is continuous at every point of the closed interval from A to B, and it's differentiable at every point of the interior interval from A to B, not including those endpoints, then there is at least one point C in that A to B interval where the instantaneous rate of change is equal to the mean rate of change. And remember, the instantaneous rate of change means the derivative. So this is saying that the derivative of f at C is equal to the slope, f of b minus f of a, over b minus a. And visually what's happening in here, we've got this chord running between points A and B. Somewhere on that curve on the inside, there has to be some C point where the slope of that tangent line, where the derivative is equal to the slope of this chord running between those A and B values. Now, if the mean value theorem fails at even one point, then the graph itself might fail to have a tangent that's parallel to that chord. So here, in this picture on the left, we've got this point A and this point B. They would create a flat horizontal line. So somewhere along here, based on the mean value theorem, we would think that there would be a place where the derivative is 0. But because there's a corner happening between these, the derivative doesn't exist at that corner. So the mean value theorem is failing on that interval, so then we're not going to have a tangent that's parallel to that AB chord. Similarly, with this picture on the right, this is an integer function where we've got these flat horizontal chunks between consecutive integer values. Now, this derivative doesn't exist at the x value of 2, so even though we've got this chord running from this 1, 1 point to this 2, 2 point, there's never going to be any place on my line with a tangent slope that is the same as these, since my lines are just flat horizontal chunks, and it's because the derivative doesn't exist at this b value of 2. In this first example, we're going to take a look at the function f of x equals x squared, and we're going to look on the interval from 0 to 2. Now, we know that the graph of x squared is just a parabola with a domain from negative infinity to positive infinity. So we know that this graph is continuous on the interval from 0 to 2, and we also know that it's going to be differentiable on that interval as well. So the mean value theorem is going to hold true for this case. So if we look on our graph, and let's say this is the x value of 0, and let's say this is the x value of 2, and let's say we had this chord connecting those two endpoints, what the mean value theorem says is there must be some c value along this interval between those 2 points that has the exact same slope as this chord. So let's start by finding the slope of that chord. And we're going to need some ordered pairs. So if we plug in the x value of 0 into x squared, we're going to get 0. And if we plug in the x value of 2, square that, we're going to get 4. I want to find the slope of this chord. So I would do 4 minus 0 over 2 minus 0. So this chord connecting those 2 points has a slope of 2. So there must be some instantaneous point along this curve where the tangent line, where the derivative, has a slope of 2 as well. Well, if we look at doing the derivative of this function is 2x from using the power rule. So if we want to figure out where the derivative is equal to 2, I'm just going to take the 2x and set it equal to 2. So at the x value of 1, this tangent line right in here has a slope that is the exact same as this chord connecting the 0, 0 point to the 2, 4 point. those two lines have to be parallel to each other. In this example, we're going to look at a couple of functions, and we're going to explain why each of those functions fails to satisfy the conditions of the mean value theorem on the interval from -1 to 1. So here in this first part, we're going to look at the function square root of x squared plus 1. Now we can actually do a little manipulating with this function, because anytime you plug in an x value, regardless of if it's a positive number or a negative number, if you square it, it's always going to give you a positive answer, and then we're assuming a principal root here, so then we're going to get a positive square root of whatever that x value being squared was. So what's going to happen in here when you square root this x squared, because of all that positive stuff happening there, this essentially is the exact same thing as the absolute value of x, but then we still have that plus 1 on the end. Now if we think about using this interval from -1 to 1, and we plug in each of those x values, well, if we plug in -1, do the absolute value of it, that turns it into positive 1, but then add 1, we'd get 2. And then if we plug in the other end value of positive 1, absolute value of 1 is 1, plus 1 is 2. So then if we found the slope between these, this would say 2 minus 2 over 1 minus -1, so we'd get 0 over 2. So between these two endpoints of our interval, we've got a slope of 0. So if the mean value theorem works, then there should be some place on this interval where we have a slope of 0. But we said that there was going to be a problem with this. This graph, this absolute value graph, absolute value of x plus 1, well, we know that an absolute value graph is a V-shape, but this plus 1 is going to shift this up one space. And we were talking about these 2 points at -1, 2 and positive 1, 2. So that flat horizontal line. But the problem with this function on this interval is we've got this corner happening in our graph. And functions are not differentiable at corners. And in order for the mean value theorem to work, your function has to be differentiable on the open interval between the endpoints that you're looking at. And this one is not, because we're not differentiable at 0. So this function fails to meet the necessary conditions for the mean value theorem. Now in this part, we've got a piecewise defined function. We've got x cubed plus 3 for x values that are less than 1, and we've got x squared plus 1 for x values that are greater than or equal to 1. Now what I'm going to do is actually graph this out so that we can see what's happening with this piecewise function. If we were to type this out in our calculator, we would get a picture that looks something like this. So on the left-hand side, that blue portion of the graph is the top piece of the function, and the red portion of the graph is the bottom piece of the function. Now, one of the conditions for the mean value theorem said that your function had to be continuous on the closed interval that you're looking at. So this graph would have to be continuous on the interval from -1 to 1. But we can see as we look at the x value of 1, there is a discontinuity happening within the graph. So because this function is not continuous at that x value of 1, then it's not meeting the necessary conditions for the mean value theorem. In this example, we're going to take a look at the function f of x equals the square root of 1 minus x squared, and we're going to look on the interval from -1 to 1. And what we want to do is find a tangent to our function f that's on the interval from -1 to 1 that is parallel to the secant line AB, where A is made up of the point -1, f of -1, and B is the point 1, f of 1. The first thing I want to do is graph this out to make sure that it meets the conditions for the mean value theorem. So in my y equals, I've got that function typed in. I'm going to adjust the window a little bit. I'm going to go from -2 to 2 on my x's, and from -2 to 2 on my y's as well. Now the graph is going to be a little bit stretched out horizontally, but this is actually just half of a circle with a radius of 1. We can see from the graph that it is continuous on the interval from -1 to +1, and it's also differentiable on that interval as well, because there's no corners or cusps or discontinuities or any of that stuff. Now, it's not differentiable at the endpoints of -1 and +1, because those would have vertical tangents, but it doesn't have to be differentiable at the endpoints It just has to be differentiable between the endpoints. So we're okay as far as the conditions of the mean value theorem go. So now what I'm going to do is go through and find where these A and B points actually are so that we know what slope we're looking for. So for the A value, this says that we're going to plug in an x value of -1 into our function. So -1 squared is 1, 1 minus 1 is 0, and the square root of 0 is 0. So that's at the point -1, 0. B, we're plugging in an x value of +1. So 1 squared is 1, 1 minus 1 is 0, and the square root of 0 again is 0. Now if we find the slope between these, 0 minus 0 over 1 minus -1, we get a slope of 0. So we're going to be looking for a place where the tangent line, or where the derivative, is equal to 0. So now what we're going to have to do is go through and actually find the derivative for this function. Now we've got this square root on here. To find the derivative, I'm going to rewrite this as a 1/2 power. So this is going to be 1 minus x squared, all raised to the 1/2 power. Now to find the derivative, I'm going to use the power rule. So I'm going to drop that 1/2 down as a multiplier in front. I'm going to leave the stuff on the inside alone for right now. Subtract 1 from the power, and that becomes -1/2. But then because we've got stuff happening inside of our parentheses, we have to remember to do the chain rule. So if we do the derivative of what's on the inside, the derivative of 1 is 0. With this x squared, if we drop the 2 down, this becomes a -2x using the power rule. Now I'm going to simplify this down a little bit. I don't like having that negative exponent, so I'm going to put that on the bottom of my fraction with the 2. Across the top, we're just going to have the -2x. So this is going to say -2x over 2 times 1 minus x squared to the 1/2 power. We can cancel out these 2's on top and on bottom. So then we're left with -x over 1 minus x squared, all to the 1/2 power. Now we could rewrite this 1/2 as a square root, but it's not necessary to do. What we're trying to figure out is where this derivative would equal 0. So I'm going to take that -x over 1 minus x squared to the 1/2 power and set it equal to that 0 slope that we're trying to find. If we took this denominator and multiplied it over to the other side, then this would just say -x equals 0. So then at the x value of 0 is where our derivative is equal to 0. Now if I want to figure out the actual point where this is happening, then I would go back up to my original function and I would plug in that x value of 0. So 0 squared is 0, 1 minus 0 is 1, and the square root of 1 is 1. So this point is happening at 0, 1 on our graph. So if we were to sketch out this graph, we said that our function was going to be half of a circle with a radius of 1. We were looking at these endpoints. So we had a flat horizontal chord connecting those. And we just figured out that at 0, 1, our graph would have a flat horizontal tangent line. And that would be the line y equals 1. Now, all the examples that we've been doing up to this point have been very mathematical and conceptual. But here, if we're talking about a physical interpretation, if we've got a car accelerating from 0 and it takes 8 seconds to go 352 feet, then its average velocity over that 8-second interval would be that 352 feet divided by 8. So that would be 44 feet per second, which roughly equates to 30 miles per hour. So because of that, and because of the mean value theorem, at some point during that acceleration, the mean value theorem says that there had to be a specific point along that interval where the speedometer read exactly 30 miles per hour. So what's happening here, if we think about this graphically, we've got a car that starts at 0 and it's accelerating and driving away. Well, if we think about this horizontal axis as our time and our vertical axis as the distance traveled, because this car is accelerating, then as time goes on, it's going to travel a further distance. So on this 0 to 8 second interval, we averaged about 30 miles per hour. So the mean value theorem says that there has to be somewhere on this curve where we were going exactly 30 miles per hour. That's going to be it for this video. Thanks for watching.